In this video, we're going to go over number 36 on the review for the acids and bases, where we're doing a titration of methylamine with hydrochloric acid, and we're asked what the pH is at the equivalence point of the reaction. So the equivalence point is when we've stoichiometrically neutralized a base with an acid or vice versa. In this case, we know the volume and molarity of the hydrochloric acid we're using to neutralize methylamine, which is a weak base. So when we're looking at the pH of this, since we have a weak base and a strong acid, we would expect the pH at the equivalence point to be below 7 because it should be acidic. Hydrochloric acid is stronger than methylamine. So what that means is at the end of this titration, what we're going to have left in solution is basically the methylamine having gained a hydrogen and the chloride ion floating around. So the challenge is weak bases have relatively strong conjugate acids, and relatively strong conjugate acids are going to contribute some hydronium ions to the solution. So we're going to look at what that does to the pH. So given that we know the volume and molarity of the hydrochloric acid we use, we can figure out how many moles of the protonated methylamine that we have right here, the conjugate acid of it, right? So now we had 25 mils of the methylamine solution, 40 mils of the hydrochloric acid solution, giving us a total volume of the solution of 0.065 liters or 65 mils. Given that we basically produced 0.00400 moles of the protonated methylamine, we calculate the molarity of the protonated methylamine that we have at the end to be 0.0615 molar. So then we're going to look and see what that does to the pH of the solution. Now, since that's floating around in the water, and again, strong acids have very weak conjugate bases, the chloride basically does nothing. So we're going to look at the impact of this. We're going to create an ice chart or rice table, whatever you want to call it, looking at how much hydronium ion is going to be produced, and we're going to look at what the pH is there. So we're going to assume we start with a molarity, an initial concentration of 0.0615, which is what we got from there. Some amount of that is going to ionize, and since that's going to be a negligible amount, and we'll see why in a second, that's going to be the final molarity of this. Now, in order to determine the Ka, in the problem we were given the Kb of methylamine, because it's a base, the Ka of the conjugate acid is going to be equal to 10 to the negative 14, or Kw, divided by our Kb, because the product of our Ka of the acid times the Kb of its conjugate base gives you 10 to the negative 14. So we're able to determine our Ka value there, and we're assuming that however much of this ionizes is going to be how much hydronium ion forms, as well as going back to the methylamine. So now, writing our Ka expression for this, we have hydronium ion concentration times our methylamine concentration over our protonated methylamine. I should have put that in brackets, and I will do that now. All right, so we have X to represent both of our concentrations in the numerator. We have 0.0615 as our concentration of our denominator, and that's going to be equal to our Ka value. So when we solve for X, we use X to represent our hydronium ion concentration, which means that we can use that to calculate our pH. So when we solve for X, we get that it's 1.18 times 10 to the negative 6. The negative log of that value is 5.93. And therefore, we can say that the pH at the equivalence point is 5.93. And we would have expected it to be acidic because again, strong acid, weak base, we'd expect the pH to be below 7 at the equivalence point.